our next speaker is GFDW02 Bach. And I guess you're going to be talking about mixing like various kinds of information for forecasting.
Yes.
Okay. Thanks.
Thank you. And thank you to the organizers of the conference. It's been really nice and for inviting me to speak. So I'll be talking about some work I've been doing about combining physical and data-driven forecasts. So what is the motivation for this? Well, there's been a lot of interest in machine learning for geophysical prediction because it can bypass existing model errors by learning directly from data. And I'll use machine learning and data-driven forecasts interchangeably here. But the question is really, how do we use these ML forecasts to improve both forecasting and data assimilation? So I'll be talking really about machine learning forecast models. I won't be talking about other applications of machine learning like subgrid scale, parameterizations, etc. So of course, the obvious thing is if it's better than the physical model, then we'll just replace it with the physical model. So that's probably not going to happen anytime soon, except maybe for specific cases like nowcasting precipitation. And you know, if it's the machine learning model is better in some ways, so in predicting certain features, dynamical modes, for example, then we want to combine optimally the information either in both of these forecasts. And then the other option is, you know, if the machine model is worse, but it's still cheaper to run, as it often is, we can use it, hopefully, you know, to increase our ensemble size. We can maybe get a better estimate of the forecast PDF, as well as estimation of covariance matrices and data assimilation. So I'll just mention quickly, I won't talk about this work, but in this preprint, we applied a machine learning forecast model to augment ensemble size in data assimilation with the quasi-geostrophic model. And so maybe this could mitigate the need for localization in the long run, which is pretty ad hoc. So I'll be talking about two main projects. So this first one is about leveraging predictable modes to improve South Asian monsoon prediction. So as the last presentation talked about very nicely, so beyond the weather timescale, we have several sources of predictability. So these include Madden-Julian oscillation, monsoon interseasonal oscillation, extratropical oscillations, for example, on the subseasonal timescale. And these modes are generally more predictable than the overall state. So much so that, you know, the data-driven forecasting methods have been developed for these modes, and they're often work better than dynamical models. The question is, how do we use these forecasts to actually improve our forecast? Generally, these modes only comprise a portion of the variance, so we can't invert and go back to a forecast of the full state. So I won't go into details about this method. I'll just show some results, but we propose this ensemble oscillation correction, the essence of which is if we have an ensemble forecast, we can weight the members by their distance in the subspace corresponding to the mode of interest. And this is a paper we had in the Journal of Climate that's describing the method and showing some examples on toy models. But here I'll show actually some results for the monsoon. So just a short introduction. So the monsoon interseasonal oscillations are these large-scale rainfall anomalies that propagate northward across the Indian subcontinent. And these are pretty important to get right because they characterize the active and break phases of the monsoon within the monsoon season and much of the regional rainfall patterns. The dominant oscillation has a period of about 45 days. So I'll just show this video. So this is the monsoon interseasonal oscillation for a particular season, extracted from outgoing long wave radiation data. So you can see this very large scale and pretty predictable structure, right? This northeast propagating structure. Yeah, so, so various studies have shown that these are quite predictable. Just an example from this paper, Krishnamurthy and Sharma 2017, in the bottom part of the panel is the CFS prediction of this meso mode. You can see it's all over the place. And in the top panel is a data-driven forecast. So here, what we did is first extracted the meso from rainfall observations using multi-channel singular spectrum analysis. And I won't be talking about details of this, but it basically forecasted this mode with a very simple analog-based method in the subspace. And in terms of the forecasts we're correcting, so these are the IFS forecasts, actually the seasonal forecasts from the ECMWF. This is starting 1st of July, August and September, and we use 9 years. This is 25 ensemble members, and this is really just to make the point that this is a good baseline. This is really the state of the art in subseasonal monsoon prediction. It really outperforms all other models. So we'll verify against reanalysis, and I'll just show some results in terms of the temporal correlation as well as the RMSE skill score. RMSE skill score higher is better. So here is just the forecast of the meso mode. So we can see that we have pretty good skill for a month or longer of just this meso mode. And then here is the effect on the precipitation forecast. So in the top half we have so this is the temporal correlation of in the top half over all the monsoon region, and on the bottom over India specifically. The orange is the corrected forecast. We see, especially in July and August, significant increases in the temporal correlation by doing this correction. And then with the RMSE skill score, we also see improvements. So just to conclude this part, so we applied this ensemble oscillation correction in South Asian monsoon, and can show that this, we can use this to improve operational forecast. So this is really a proof of concept that these data-driven forecasts are useful and can help us improve physical forecasts. Oh, sorry.
Can you just say a few words on the data-driven forecast is actually using?
Yes.
In terms of the two-dimensional forecast?
Yes. So it's actually, so we once we're in this subspace of the interseasonal oscillation, it's just analogs, and that's so it's a well, actually, we did some dimensionality reduction, so you end up with a two-dimensional space, and you just do analogs, analog forecasts in that state. So in that space, so it's very simple. And there have been various other methods that people have applied to do these kind of forecasts. In general, in general, they're.
But then it's purely Markov. I mean, like you take the best analog, and then
Or several analogs, but yeah. Yes.
What's your analog distance?
I mean, the analog distance is just L2 norm in this two-dimensional space. Yeah. So really, more the non-trivial part is actually projecting the forecast into that space. So basically, because it's a filtering method, you need both the it's like a backwards forwards filter, the signal spectrum analysis. So you basically need future information. So you can only approximate the projection. So this is, of course, I didn't cheat and use future information, but I just it's an approximate mapping that I did with a neural network in order to map into this space. But I mean, I know there are various other methods for this that might be simpler. But more generally, so this is a case study of combining these physical model forecasts with data-driven forecasts, and the question is, how do we generalize this idea? So now I'll talk about some work with Michael Gill on multi-model ensemble common filter. And so, so this is this is a scenario where we have multiple imperfect models of a system, as we tend to do. We have, we can get a lot by combining model forecasts. I mean, especially in climate prediction context, multi-model ensembles have been very successful. But really the motivation for this work was, we could use a generic method like this to combine physical and machine learning forecasts as well as multi-fidelity forecast, et cetera. And we want to combine the multiple model forecast as well as observations. So it's multi-model data assimilation. So equation 2 is the standard Kalman filter cost function for the assimilation steps. So we have our control variable X, we have our forecast XF, we have the corresponding forecast covariance matrix, PF, and then we have the observation terms, observations Y, and observation error covariance R. So now we can consider a generalization of this to multiple models. Now we have capital M models, and we have each model has its own forecast state, XFM, forecast error covariance matrix, PFM, and we also define these operators GM. So we want to compute the analysis in some space, and these operators will map from this reference model space to the model space of model M. So just a quick schematic, we're really going from the on the left, which is the typical single model forecast assimilation cycle, where we have our forecast distribution, our observation distribution, we combine it into the analysis and then run the forecast for the next time. Now we go to the right, we have multiple forecasts, observations combined into the analysis, and then forecast with from the analysis with the different models. So something nice about this this multi-model common filter is you can show that it can be solved in an iterative method using any single model DA method. So this really allows us to use existing methods that we have. It's really the most natural generalization of the Kalman filter. So I mean, it generalizes the cost, the variational viewpoint, like I showed. We also show in our paper that it's the minimum variance unbiased estimator for multiple models, and it also generalizes the Bayesian formulation of the Kalman filter. Just to note, if anyone's familiar with the supermodeling idea, where multiple models are synchronized to each other, this can actually be seen as a form of that also. If you take the synchronization view of data assimilation. So this can be used also for forecasting if we neglect the observation term, and for longer forecast horizons, we can repeat this recursively at intermediate forecast horizons. So again, I won't talk about the details of this, but we implemented an ensemble version of this, so call it a multi-model ensemble Kalman filter. I like to think of this really as kind of a unification of multi-model ensembles and data assimilation, and it provides a principled way to combine models for DA and forecasting. So just to note, we have to do model error estimation to do this properly. So we typically think in the common filtering literature of the forecast covariance matrix as being composed of predictability error that's due to the error in the initial conditions, as well as a model error Q. So we need these estimation of these Q matrices or adaptive inflation alternatively. So there's methods to do this. We used a very simple innovation-based method I won't go into, but I'll show some results for Lorenz 96. So we have 4 imperfect models with errors in the forcing. And then I'll show results comparing the multi-model ensemble Kalman filter to regular unweighted multi-model ensembles, as well as single model ensembles of the same size. And this, we use as a component method, the ensemble square root filter with localization and estimate model error concurrently. This is in terms of CRPS, which we've had a few talks on. So you can see that the analysis CRPS for the multi-model ensemble Kalman filter does significantly better than any of the individual models, as well as the unweighted ensemble. And the 2 green ones are just different variants of the multi-model ensemble Kalman filter. We also see this for forecasting. So if you look at the CRPS versus lead time, the multi-model ensemble Kalman filter can do significantly better than any of the models and the multi-model ensemble. I'll show maybe a more interesting form of model error. So for this, we use the 2-scale Lorenz 96 model. So here we have large scale and small scale variables that are coupled. So each of the large scale variables has a certain number of small scale variables associated with it. So let's say we want to combine forecasts of 2 different models. One is a higher resolution than the other. So the low resolution models will have error due to unresolved scales. And then when we use the multi-model ensemble Kalman filter, we can get combining these 2, we can get an analysis that's more accurate on both the large and the small scales than either model. So in conclusion, we developed this multi-model ensemble Kalman filter as a versatile method for multi-model data assimilation and forecasting. And this can significantly outperform unweighted multi-model ensembles and the best model. So now the ongoing work I'm doing is testing this as to combine physical and machine learning forecasts. And in the future, in terms of this framework, we want to account for correlated forecast errors and derive the smoother version of this. And there's open source Julia code available if you're interested. This is in the archive paper. It's currently under review in James, so hopefully it'll be out. It'll be out soon. Thank you.
Thank you very much. Do we have any questions? Yeah, I can say.
Just a quick clarification. So last slide showed us goals system. I'm not sure I understand if you explain why the combined forecast is better than high resolution. What's really combined?
Sorry, so I should have said there's also, so there's error in the forcing. So the two models have two different types of model error. So I did one that has the unresolved scales and then one that has error in the forcing. But basically, I mean, the intuition is that the small scales actually benefit from additional information about the large scales, even if the model is not, the second model is not simulating them explicitly. We allow information exchange between the small and large scales in the data set. It's just a one. Oh, so low resolution is low resolution is actually just having none of the small scales in this case. I mean, it would be interesting to do a case where we add some kind of parameterization for the small scales, but we didn't do that here. So this is just the large scale variable simulated. Yes.
The question is, if you look at this cost function 3, what you are actually doing is, if you add more and more models, the energy will be sliding to the left. And so what you're minimizing in effect is actually you throw away more and more observations.
Yes. So this is.
So in some sense, should somehow scale also the cost function the data more.
Well, yes. So the issue is that within this framework we haven't implemented correlated forecast errors yet. So we assume that each of the model forecast is an unbiased, independent estimate of the state. So you should, if you add more model forecasts, you should actually put less weight on the observations. But in practice, these are not unbiased and independent. So what I didn't discuss is we also do an adaptive inflation scheme for the combined forecast, so that just reweights the two components. Yeah.
See how much percentage is due to that model.
Yes, I mean, so you actually do get, yeah, I mean, you can reconstruct it. I mean, it's, you get like basically linear weights on each of the models, so you can. Yes. Yeah, so you can. Yeah, that's a good point. Yeah. Sebastian?
Actually, when you have a question, you have to come here because I think they don't put the.
But isn't that what you're doing effectively, sort of a Gaussian mixture modeling? I mean, assume that all the models are identical. Then you have each of the models you treat like a Gaussian. And then you take the sum of this. It looks to me like you're actually doing inference over a Gaussian mixture. And then approximating this by Gaussian approximation again? I mean, I didn't see all the details, of course.
Yeah, I mean, it's a good question. I haven't, I haven't thought about it, but it would be, it would be interesting to see if you get the same, you get the same results if you assume a Gaussian mixture instead of independent forecasts. Yeah.
I mean, of course, if you then ensemble come up with approximation, right? So that gives you different results.
Yes.
But it might also explain different ways for each of the models.
Yes.
So that is how
Yeah.
how good each mixture is.
Right. Yeah, that's a good point.
Sure, can I just throw in a remark from the first bit of your talk about
Yeah.
machine learning?
Yeah.
Estimated model error seems to be a very good place for machine learning. You're really doing things. Models have done their best, and there's still an error.
Yeah.
Machine learning should be a very good way of trying to estimate model error.
Yes. Yes, I think that's true. I mean, because you're essentially bypassing the error in the models. The issue is the data availability question, right? So there have been all these kind of estimates. How much data do we need to be able to to come up with machine learning models that can outperform operational forecast models, and it's like immense, like orders of magnitude higher than all the data we have. But I think that's really more for the kind of synoptic scale, synoptic scale like mid-latitude weather. I think there are other sources of predictability, as the last speaker also suggested. Even just with this monsoon thing, we see that there are other sources of predictability. I think that we can learn using machine learning, and especially for like seasonal forecasting when the drift is such an important element. I think there's a lot of room there. Yeah.
Do you want to come closer? You even farther?
Yes.
Because the microphone doesn't work.
In my sense, in some sense, my question is also related to what Wilhelm and Sebastian are asking. So this first of all, this why here? What do you observe? You observe what is the truth? Is the truth any one of those four models, or is it a different model?
I mean, so in this, in this case, in the numerical experiments I showed, at least, I didn't use any perfect models. They were all perturbed. They all had different model errors.
But what is it that you observe?
Well, you make observations of the true system, right? Like
what is the true system? Is the true system any one of those four?
Not necessarily. I mean, it could be. I mean, in a real situation, you wouldn't do that, right? But you would observe with satellites the Earth system.
What is it in your case, in your particular case?
I'm not sure I understand. So,
what is it that you observe?
In the numerical experiments? Yes. So in the numerical experiments, I do observe the real system with noise.
And the real system, is the real system one of these four?
No.
No.
Yeah.
Good.
Yeah.
Now, it makes sense to put weights in front of each of the four terms that you have for each of those. Because, and I think it should be a complex combination. The sum should be one.
Yes, it is.
Otherwise,
yeah.
As Wilhelm said, you shift the onus on the first term, and you begin to forget the second term, the term with the observation, if you do this.
Yeah, I mean, so we show in the paper it is what you get is in fact a convex combination of the different model forecasts and the observations.
So put it differently, if you divide by 1 over m, so that we have the same thing. Essentially, what you have, the weight on the observation term is a order 1 over m. So you lose.
Yes. Well, I mean,
observation term.
So again, if you make the assumption of that the forecasts are independent, unbiased estimates of the true state, as you do in a typical Kalman filter scenario, then that's a desirable feature, right? Because you're getting more information from your forecasts as you add more forecasts, and you put less weight on the observations. But in practice, because these are not independent estimates, then you'll want to temper that somewhat, right? So the next part that I want to do is account for correlated forecast errors, such that, I mean, if you have perfect correlation between two models, then it doesn't give you any new information, right? But to the extent that it is independent from the other model forecast, then it does give you new information.
To be discussed.
Right. Yeah, let's
Now,
discuss.
can I ask one more question to them, or then I stop? So, you know, for the first example,
Yeah.
From experience, the size of the analog dictionary is crucial.
Yeah.
Did you find the same? Did you draw the same conclusion? And what was the size of your analog dictionary?
So I didn't do I didn't do tests of reduce using different sizes. So the size was actually very big. It was since so it was, I mean, it was almost 100 years of data, which is kind of we don't really have that everywhere, right? But this is this gridded rainfall observation data set over India. It goes back to 1901. So we have pretty good data in that case.
And the data is
It's trying to remember. I think it might be 6 hourly or something like that.
Oh,
yeah.
okay.
Or
Okay.
yeah, I can't remember.
This is good.
Yeah. Yeah.
So we can thank the speaker again. And
I'll need 2 minutes to
oh,
set everything up.
Oh, yeah. Okay, yeah.
Yeah, one more.